Hi, dudes. How's the volume? Any better? Hope so. Uh-oh, hang on. Now I'm screwing it up. Stay. Hold on. Hi. Hi. Whoa. Sorry, that was intense. So we should be all set, right? Anyway, we should have, I sure hope, talked about these pages already. The last few before here. So we've been talking about position and time graphs and what you can tell from them. All right. Let's expand our discussion to a case like this. Oh, there's a bell. Ball rolls down a hill. Yeah. Never mind. Ball rolls down a hill. Look at it go. And what I want you to do on the next page, you're going to actually pause for a couple of minutes. You are going to draw for me, sketch. I would use a pencil. Sketch what you think this graph looks like. I will remind you of the following. You know what a ball does as it rolls down a hill. You can see what it does hopefully here. But you know what a ball does when it rolls down a hill, right? We want to show that here. Think about what you know about a position, a position and time graph. And how do you show what we want to show with that ball rolling down a hill? So pause, think, and draw with a pencil. Ready? Pause. Okay, you're back. Did you pause? Did you cheat? Or did you pause? You better have paused. Well, hopefully, folks, you came up with something that looks like that. It should be a curve. All right? It wouldn't kill you to have your curve be a little sharper than mine, but I would try to make it use up most of the axes. Okay? I wish mine was a little flatter in the beginning, like that, and a little steeper in the end, like that. But what are you going to do? Now, how do we know this is what that graph looks like? Well, let's talk about that. Okay? Let's look at an instant in time where this ball has changed its position by something we call delta x. It's taken some time interval, delta t. Well, what we can look at so far is we could look at this line. Right? We've talked about the slope of lines on position and time graphs. We know that slope gives us velocity. Now, there was a time before, a few days ago, I bet when I said it's going to be rare for us to just use the word velocity. Right? We're going to have to be pretty specific about what velocity we're referring to. So if we look at the slope of this line, well, it gives us what we call the average velocity that object has experienced or had over this time interval, delta t. Because we know that average velocity is total displacement over total time. Okay? So, yeah, that slope gives us the ball's average velocity as it's rolled for a certain distance and taken a certain time. However, what if we want to know how fast it's actually going at that instant? Well, what we have to do is say, instead of looking at, in general, how far it's gone and in general how long it's taken, we have to look at really at a really small interval of time, maybe like that big. And in that little interval of time, maybe it's traveled like that far. And if you look at, I wouldn't draw all this, I'm getting a little more in detail than we need to, but if you look at this green section right here, it kind of looks like that right now, and that looks pretty much like a straight line, doesn't it? It's part of a curve, so it's not straight, but it looks pretty straight. Well, if we made this time interval delta t even smaller, and this change in position even smaller, this thing gets closer to being like that, and it's really like a straight line. But at the end of the day, if we take that little straight line and extend it like that, we get this line here. the slope of that line that we call a tangent is velocity. The slope of any line on this graph gives us a velocity, but the slope of that line, the slope of that tangent, is what we call, well, the velocity, or speed, at that instant. We call it an instantaneous. Oops. Yeah. We call it an instantaneous velocity. So it's really not a velocity over some time interval. Well, I guess it is, but it's, check this out. It's like something about this. It's like something about, well, as the limit, it's like a limit thing, where delta t approaches nothing. What I mean by that is it's not an average, because we're saying it's really only at one instant. That happens for, the blink of an eye, an immeasurably small amount of time, because at the next instant in time, it's going faster. The instant before that, it was going slower. So that's only, the ball only has a velocity for an instant. And in every instant, it's either faster than that, or slower than that. Okay? So what I want you to be able to tell is, if we look at a few different instants in time, and we look at a few different tangents and their slopes, you can see that their slopes keep getting bigger and bigger and bigger, right? Here's our first instantaneous velocity. Well, our first really is the slope at this instant, which I was trying to make nothing, right? This part of the curve right here is supposed to be really flat and then come up, right? Or at least for an instant it's flat, and then it immediately starts to curve up. So in the beginning, we can say this thing has an instantaneous velocity of nothing. If you remember, we started the ball on that hill, and it started not moving, and then started to roll. So in the beginning, we would actually say that the instantaneous velocity was 0. Right? This means initial, remember that? Well, we can see that the slopes of these tangents keep getting bigger and bigger, which means that the instantaneous velocities keep getting bigger and bigger. And it means this thing speeds up. All right? Now, check this out. Here's where things really start to get challenging. Let's look at a graph of velocity versus time. Same object. And again, we're talking about this case. Position versus time does that. Velocity keeps getting bigger and bigger and bigger. The question is, what's that look like on a graph of velocity versus time? So I'll say here, remember, hint, v keeps increasing. How do we show that here? If you want to pause. Think about it. Maybe sketch. Ready, pause. Okay, you're back. Well, this one, especially, really, if and only if this thing rolls down a constantly sloped incline like that, rolls down that incline, the graph of velocity versus time looks like that. All right, if you go back a page to where these, let me go back a page. Can I do that? Do it 12. Right, we have red dot, purple dot, gray dot, blue dot. Next page, again, we have red dot, purple dot, gray dot, blue dot. Well, if this thing rolls down a constantly inclined slope, the velocity versus time graph looks like this. And notice it says, sure, that velocity gets bigger and bigger and bigger and bigger. And at each interval of time, we should be able to characterize how much bigger the velocity gets. Well, hopefully we can tell by these intervals. Notice, the time intervals are constant. And notice also that the changes in velocity are constant. Well, I guess I just said it. All right? So we need to be able to talk very specifically or very clearly about what a straight line on a graph means. Okay? A lot of people will say, it's constant. Well, what's constant? All right. This tells us really that I would say, I would say that the velocity changes at a constant rate. So for every interval of time delta t, notice we have an equal change in velocity delta v, right? Another of those delta t's, another equally sized delta v, and so on and so on. There's another way to say the same thing. If velocity changes at a constant rate, or really we can say, this is even more, hopefully even a clearer way of saying this, velocity changes by the same amount in each equal unit of time. That's the very definition of something else. That is the definition of saying that the object has a constant acceleration. Huge idea. Huge, huge, huge idea. Okay? We have to know what that means. And here's what it means. It means those two things there. To say an object has a constant acceleration means its velocity changes at a constant rate, which means its velocity changes by the same amount in each second, or in each minute, or in each hour. Okay? Now, this gives us the definition of acceleration. All right? If we say that a constant acceleration means a constant rate of change of velocity, well, acceleration is, therefore, by definition, the rate of change of velocity. What else pops up here? Anything? And therefore, we can come up with an expression for acceleration, right? Let's back up a minute, right? Remember what our definition of average velocity was? Our definition of average velocity was rate of change of position, right? And we said that that makes it delta x over delta t, which we can just really call, and typically we do call just delta x over t. So here's the rate of change of position. Well, again, we want the rate of, which we'll just call t. I can call it delta t, no, I'll just call it t. The rate of change of velocity. Okay? Now notice, this is super duper important. Notice that it's a delta v. It's not v average, don't write that. It's not, well, yeah, it's delta v, which is very different from v average, right? This is average velocity. This is change in velocity. A change in any quantity, you've got to look at two different values of it. That's how we always do change in anything. We always do the final value minus the initial value, right? If it's, this morning it was 50 when I woke up. Right now it's 68, which means that the change in temperature today is 18 degrees. I took the 68, the final value, minus the 50, the initial value. Okay? So just so we're sure, that's how we do delta V. Now something else to notice, right? If we go ahead and maybe put this back in here, it doesn't matter if you write that when you do work or not, but if we talk about acceleration like this, and at least, write it like this, especially when we look at a graph, notice that we're talking about delta V, which is change in this stuff, and delta T, which is change in this stuff. Or we're really doing like a delta Y over delta X, or a rise over a run. So for this kind of graph, slope equals acceleration. Now, wait, we said before that slope is velocity, right? But that's for X versus T graph. Slope equals average velocity. For a V versus T graph, slope is acceleration. Fair enough? Okay. Okay, next page. Now, I had this skipped over something. What I want you to do here is write for me, please. Tell me again what constant acceleration means. Be as clear as you can. All right? Acceleration by definition, let's just refresh, is what we call the rate of change of velocity. Okay? So here's two different objects. Good. Two different objects. All right? And let's talk about how they're different. Well, what's the same for both, let's say? What's different? How about we call this object A, we call this object B. Well, same. What do they both do? Well, these both speed up. How do we know that? Well, let's look at the first instant in time. At time t equals 0, they both have speed, their initial speed, v naught, of 0. So they both start at nothing, with a speed of 0. And they both, later, v final A and v final B are not 0. Furthermore, they both move in the same direction. How do I know? Because v final A and v final B are both greater than 0. They're both positive, which means they both have a positive velocity. They're moving in the positive direction, whichever direction that is. What's different? Well, we'll do that. What's different? Well, they have different magnitude of acceleration. Right? I'll write it like this. A is greater than AB. The acceleration of A is greater than the acceleration of B, which really means in this case, A speeds up faster than B. They both speed up, right? A speeds up faster. A's rate of change of velocity is greater than B's. A's acceleration is greater than B's. Right? At some point, or at some instant, they each, oh boy, is that flat? I can't tell. That's no. At some instant, they both get to that speed, this speed here. It only takes A this long to get to that speed. It takes B a lot longer to get to that speed. Okay? What else is different? I mean, I guess we could say that, well, certainly V final A is greater than V final B. I'll go back to saying for the same, V initial A and V initial B are both 0 That's the same for both. But their final speeds are different. I'm going to say this. Here's a question for you. Yeah, question for you. Distance traveled? I go here or here? You tell me tomorrow. And you fill that in. And I say, and once I find my little clicking device that advances the slide, clicking device, here it is. And tomorrow, you do this for me. You fill in most of these except for the first one, which I'll start with. Object A. Well, object A has a constant positive velocity. That's literally the only thing we can say about object A. And what does this mean? It means moves at a constant speed in the positive direction. What's the positive direction? I don't know. Who cares? Is it north? I don't know. It's whatever someone has defined it to be. Okay? So talk to me about what object B's motion is like compared, right? Compared to object A. So compared to object A, object B does what? Things I want you to consider. Talk about speed. Talk about direction. Talk about distance traveled. Talk about those three things for each one of those. Yes? We'll get to this in class together. Tough stuff. Okay, that's your assignment along with that. Okay? Okay, people. Peace out.